So with that, I would like to introduce my friend and colleague, Professor Ishui from Stanford University. Ishui is one of the world-leading scientists in the field of nanotechnology and energy storage. He has made a significant impact in these two fields. He has published extensively in very high-impact journals, over 400 or 500. I have his old bio, so I'm not sure how much now. And he has also a spirit of entrepreneurial. He actually founded 2 companies in each of these fields, in nanotechnology and energy, so that are thriving. He's also the editor of a Nano Letter journal and has obtained many awards, and I will urge you to go and look at his bio in the web. So for the sake of saving time, I would like to share. Okay. So he will be talking about battery materials and interface understanding and design at the nanoscale. This is an area which is very, very hot at the moment, and a lot of people are very interested in the talk. So I would expect that we'll have a good audience. With that, you will have the floor.
Thank you, Kel, for the introduction. And I would like to pass my regards to everybody during the COVID-19 time. Hope everybody is safe. I'm going to talk about batteries today through material design, particularly in the nanoscale, and also these design enabled by the new tools. Since the audience is very broad, so I think for my battery friends right here, no introduction needed, but maybe just a little bit for the general audience. We know batteries are important right now, nowadays, impacting nearly every aspect of our lives. So important, this has been recognized by the 2019 Nobel Prize. Our friends right here, John Goodenough and Stan, and together with Yoshino winning this prize. Very well deserved, and also a very timely prize as well. So then after that, we ask the questions, given the lithium-ion batteries where they are today, what's next for us? Maybe I'll just say this as a battery 2.0 for us to think about. We need to increase the energy density per weight or volume by a whole lot, hopefully double, right? That's what Battery 500 Consortium has been trying to do, is to produce 500 watt per kilogram of the batteries and extend the cycle life, the calendar life from 7-8 years to, let's see, 25 years or 30 years. Huge meaning right there. Fast charging is important as well. These will enable batteries even more everywhere and speed up the EV adoption. Safety constantly coming up as so important issues. Cost, of course, needs to continue to be reduced and going down. And do we really have a method to monitor the battery health condition to know what's happening? Well, what's the strategy for battery reuse, repurpose, recycling? And what's the strategy? What's the chemistry and solution for grid-scale seasonal storage? At the end, there's other things, flexible, variable batteries. So we try to answer this question over the past 15 years since I joined the Stanford faculty and starting research program to address some of these areas. And today, let me only focus on a few, to share with you the power of materials design and a relevant landscape, and using the new tool to understand what happened. So for the high energy density, double or more of the energy, we need new chemistry. And this plot, however, is showing you the relative volume expansion versus the amount of lithium you store in the host material, the atomic ratio. Is lithium to 1:6 is current technology roughly. If you move on to 1:1, you get a lot more lithium, 2:1 or higher. The degree of volume expansion is increased by a whole lot. Do we know how to handle those materials? The answer is no, not yet. So in the past 30 years, we learned from the graphite or other lithium metal oxide is materials that are stable hosts on the lab. To the right is a new material. They're not stable. This chemical bond breaking and reformation. These host atoms move to long distance on the right. This big structure change, this huge volume expansion. So we need to learn how to deal with all these issues. That's why redesign the materials, particularly in the nanoscale, becomes so important. If we could enable this new chemistry, the possibility to go from currently roughly 250, maybe a slightly higher depending on the company, the graphite combination with MMC, this will certainly continue to go higher with what we learned about MMC doing better. And silicon coming in allow us to look into 400 watt per kilo. Metallic lithium, even higher, and lithium sulfur. If we do it right, we don't know how to do it yet. It could be even higher. 500 watt per kilogram is the what Berkeley 500 Consortium tried to target. There are other scientists in this panel. We have Shirley right here. Also, a team member in the Berkeley 500 Consortium will be talking about this as well. So let me start from silicon. This new materials is very exciting right now. Of course, it's full of problems. Silicon has this big volume expansion of 4 times, causing the materials breaking, and also instability of solid electrode interface. Once you have expansion and contraction keeps going on during charging discharging, there's no way you can form a stable interface. My group started to work on this problem roughly about 13, 14 years ago. And this is the first paper we published. It started to design the materials in the nanoscale and correlate the design to solve the problem. We have the volume expansion taking place. We want to relax the strain. We want to make the electrical connection, so we grow this nanowire off the current collector that's conducting, current collector right there. Having electron coming in and going out and relax the strain. This was my first graduate student, Candice Chan, after I joined the Stanford faculty, now currently a faculty member at Arizona State University. So we work on this idea together. And from day one, we start to see the power of designing materials in the nanoscale. Of course, nanomaterial has a lot of problems like high surface area and so on. Its cost is high, that needs to be overcome later. And we adopted a tool very early on in about a decade ago, is to use in-situ TEM. So I keep emphasizing the tool. That's important for us to understand what's happening. So with this holder of TEM holder, there's a piezoelectric control. We can mount the nanostructure such as nanowire to the tip and apply a voltage right there, forming this nanoscale batteries. You can drive lithium coming in, electrons coming in, lithium diffusion, and start to react with silicon to look at the lithium reaction process with the materials in real time. And you can put the particles right there. You have diffusion pathway to make this happen. This is a collaboration with my colleague, Biognics, my earlier graduate student, Matt Madell, who is has been a faculty in Georgia Tech for 5-6 years now. For example, this is a silicon nanowire, 200 nanometer scale bar right here. We start to insert lithium, so we speed up this by about 5x. You see the volume expansion of silicon taking place, and there's a coating of copper, that's a black color, on the surface. And the lithiation taking place, this expansion is so powerful and crack the copper coating. And we use this tool to study the size dependence, fracture behavior. This is a silicon particle, 800 nanometer in diameters. Once you put lithium in, you see it in the center right there. It's big, surrounding this particle is some small one. And the small one actually is a lot more robust. They don't break, they don't accumulate the stress to the degree to break this particle. However, this bigger one is broken. There's a size-dependent stress accumulation in this particle we analyze in this publication in advanced materials. So the observation was the smaller particle, they don't break the critical breaking size roughly about 150 nanometers for the particles. The wires is about 300. This detailed reason of why wires is slightly bigger. This is stress accumulation across different dimensions that could explain that. The size identified using this method is important. That can guide us with the material design, how small we want the particles to be in order to avoid the breaking. So with this, we have been through more than a decade long of material design, starting from the wires, using the core shell to enhance the stability, and hollow structure to relax the strain even better. And to build a stable interface, we need to avoid the volume expansion towards outside. So we designed this double wall hollow structures. The silicon in there expand towards inside instead of outside. The red color coating with the wall force the volume expansion towards inside and form the stable interface. And we also, with time, we also go down to the low cost version, go down to the micron particle, even they're breaking. Make sure they break inside a framework so they do not destroy the surrounding environment, still allow you to build a stable interface until nowadays. I won't repeat everything. But I would say designing a nanoscale is so powerful, but this problem I mentioned earlier, the high surface area of a nanostructure reacting with electrolyte. This generation 8 of design to packing the silicon particle together into secondary particle is actually a very powerful concept. You coat it outside of secondary particle with a coating, prevent electrolyte to come in. And also nanostructure oftentimes very hard to pack nicely to have high volumetric capacity or high volumetric density. But if you pre-pack them together, it is possible to realize the potential of silicon still having high volumetric capacity right there. We show that's possible. So with all this learning, about also 12 years ago, I found the Amprius. Amprius has been taking my silicon nano anode technology into the doing R&D, doing manufacturing, and develop into the market. They supply the battery to the Airbus, the Cyphers S drone, and breaking the world record flying time. This is actually very high energy density of battery, getting to a 430 watt per kilogram range. The volumetric capacity, the energy, volumetric energy, I want to emphasize. So people often think, you have the nanostructure right there, you cannot pack, but you can do it to a way you can get to, Amprius can get to actually 1,300 watt per liter, right? Compared to your phone right now, typically a good phone is about 700 watt per liter. In terms of volumetric energy density, it is possible. So Amprius will need to do something better job in cost reduction for the silicon anode. It's indeed quite exciting time. Many of you have seen the Tesla's announcement to move full speed into silicon. And you are going to see more industry use silicon more and more for the coming decade, continuously every year. So we'll see down the road. Then we say, well, after silicon, what's really the anode you want to have? Lithium metal has been considered as the holy grail of the battery's anode. And lithium metal doesn't carry, heavy holes. The atomic ratio, if it's pure lithium metal, you don't have a holes right there. And the energy volume, gravimetric, volumetric, they're all very attractive. However, plating lithium through this plating and stripping process during charging discharging, it's very hard to control because you don't have a hose. The plating, you lose control, and you cause surface curvature change, the cracking of the solid electrode interface causing the hot spot formation. This can shoot out filamental structure, and oftentimes in form of dendrite. Dendrite is a dendritic, right? This branching structure. Sometimes it have branching, sometimes it's not. People start to mix up these terms. That is fine. And when you do the stripping, you can strip away. You also lose control. You can strip, breaking these filamental structure from the bottom or from the middle. You lose control. And you lose lithium metal very fast. You keep forming the solid electron interface because this surface area keeps changing with the electrolyte. So during this process, the volume fluctuation is very big. Every 1 million hour capacity per centimeter square is 5 micron thick of lithium. So the volumetric fluctuation for each layer reach a 15 micron or more because of capacity per unit area you're cycling is really that big. So this huge fluctuation together with high chemical reactivity, these are the two, well, in our mind, is two root causes we need to take care of in the middle. Many things are surrounding phenomenon right there. And we need to design strategy to solve this problem. At Stanford right here in my group, I work together with Professor Steve Chu and Professor Zhenan Bao a lot, and also a few other faculties as well. So in 2016, we designed a concept and publishing the first time is to have a stable host. Just like graphite hosting lithium, silicon hosting lithium, now we have a metallic lithium host. And we publish a number of papers to illustrate this concept. And also stable interface to control the chemical reactivity is very important. This interface need to be chemically stable and mechanically resilient. And we have come up a number of different strategies how to form the interface, whether it's inorganic coating or is new type of organic polymer. This is not finished task, still going. So both of them are still going. And let me share with you some of the key findings right here. Well, one key finding to really underline the concept of host is you have a controlled deposition of lithium to the location you want. So in 2016, in this Nature Energy paper, we show, for example, copper, if you plate lithium, there's a nucleation barrier and the voltage curve and then plating taking place, 40 milliwatt under the 10 microamp, very low current density, 10 microamp per centimeter square current. And gold has no nucleation barrier right there. Certainly there's two categories of material. Some has nucleation barrier, others don't. And what's the reason behind this? This turned out to be related to phase diagram. For the case of copper, on the lithium, pure lithium metal side, right? Copper has no solubility in pure lithium, but gold has some solubility. What that means is the lithium coming in has ability to dissolve gold away, but not copper, right? That's why copper can be used as current collector. So lithium and copper has different crystal structure. Nucleation of lithium on top of copper has nucleation barrier. Lithium dissolve gold away, make gold more and more look like lithium. So there's no nucleation barrier right there. If that is the case, we could use different material to control where lithium would like to nucleate. That underlines the powerful concept of the nucleation into a host. In this case, we construct a carbon host. We also found for the carbon, there's a nucleation barrier right there. Gold, nanoparticle seeds you put in, there's no nucleation barrier. You can have lithium diffusion, electrons coming in, lithium deposition happen inside the hollow carbon instead of outside. Now spatially, you have a control where lithium will go. Then this carbon would help to form interfacial layer to react with electrolyte. You possibly can build a stable SEI. So that's the underlying concept. So we made these structures using templated method. Let me also mention, to make this carbon using templated method, you don't want to have big pinholes, very big one, and this hollow carbon sphere. Otherwise, the electrolyte is going to leak in and go inside. So you want those nanoscale pinhole. You can still etch away silicon oxide, use this template, and then this pinhole will be sealed once you form the SEI. So one thing to also mention, this carbon is, of course, it's all type of carbon. If you carbon, you put in a lot of polar functional group, oxygen, nitrogen, and they start to like lithium, then lithium nucleation might happen also on carbon as well. Let me go down and then I will show you, the so-called wettability with lithium metal, the affinity with lithium metal, depending on what type of carbon you use is important. So we made this structure with a gold seed particle inside. this hollow carbon sphere in the order of about 800 nanometer in diameters also. Using in-situ TEM, again, the tool is very important. We were able to observe lithium coming in, plating in this dry in-situ battery cell. You see the gold nanoparticles in the middle. Lithium metal coming in, dissolve gold away. And then once you strip lithium away, this gold nanoparticle will come back. You'll see it in a few seconds. This is really trying to show you the concept of this phase diagram of lithium can dissolve gold. So using seeded at the bottom of this hollow carbon gold end there, we could deposit lithium up to a certain capacity, only lithium going inside. The top case is hollow carbon without the seed. And you see the filamental lithium metal deposition outside, really proving the concept CD growth spatially control where the lithium will go. So the bottom case allow you to cycle the battery during charging and discharging with much better stability. So with this type of host concept, we extend into, can we generate lithium metal inside a host without using electrochemical deposition, but during chemical synthesis? This motivated us back in 2016 to develop a molten lithium infusion into host materials. But what's the host materials to use? We use carbon nanotube film, carbon fiber, mesoporous carbon, carbon nanofiber right here. So you see, once you melt lithium, try to get lithium going to those structures. They don't like to wet. Lithium in the molten state, this is inside glass box, of course, molten lithium is dangerous. You need to do it in the environment. So they don't like to wet materials. So when we try graphene oxide, a lithium metal melt and then it wets inside. This wetting phenomenon, we call the new term to describe this called lithophilic. An analogy to hydrophilic, the opposite phenomenon will be lithophobic, right? And an analogy to hydrophobic. So the reason this can wet is graphene oxide has a lot of polar functional group react with lithium metal. That's why I emphasize as depending on what type of carbon you have, and the nucleation behavior could change, the wetting behavior could change. So with polar functional group right there, you can promote the lithium metal wetting in the molten state. If it's a solid state, it would like to deposit a nucleate. So with very lightweight of graphene oxide, 8% by weight, this host material is very small amount. We could melt lithium and let it go in. And then once you strip lithium and deposit lithium, you have to deposit them back into the host. You minimize the volume fluctuation during deposition and stripping. This we find improve this lithium metal electrochemical behavior a lot. So I won't go into detail of that. So then we also go deeper. We said, well, this graphene oxide, depending on if it's a horizontally aligned, you build a battery cell stacked like this, right? And then the lithium need to go into the host, need to go around. If you can orient it in a way vertically, and this in scientific term is tortuosity issue. Tortuosity vertically aligned will be smaller, will be one. Horizontal one will be bigger. The path need to go in will be larger. It's still dependence. We actually produce using a freezing method and this graphene oxide solution. If you freeze from the bottom, ice crystal nuclei at the bottom, right? This is aqueous solution. You can vertically align graphene. If you cool it from the side, you horizontally align. If you cool it surrounding in a surrounding way, it's going to be randomly aligned. So we generated different alignment orientation, vertical, horizontal, and random, and compare their electrochemical behavior. And the conclusion is vertically aligned is so much better because low tortuosity, lithium deposition is more uniform along the side wall. So you don't accumulate lithium on top surface of the electrode. That will be the case for the horizontally aligned. It will deposit more on the top. I will not go into detail of that. Let me also emphasize with remaining time, electrolyte is very important. You are going to hear about this from the super expert from Kangxu down the road. and how to design the electrolyte. So we went and moved into this direction about 2 years ago and really look at the electrolyte design. The reason is, in my lab, we start to develop a few tools that's so powerful, allow us to understand the interface better. One of them is a cryo-EM. I will mention in a few minutes, and you're going to hear about this more from Shirley Meng. So we start to work on this fluorinated carbon. You know, there's all kind of fluorinated molecule working better. What turned out to be this FDMB molecule to the right? It's from DME, only 2 carbon in the middle, now become DMB with 4 carbon. Now we add in fluorine only in the 2 middle carbon right there. Well, we find out, you know, it's a cathode. Oxidation stability is much better. And then on the anode side, for the lithium metal deposition, the Coulombic efficiency, basically, this is probably the molecule scored the world record in terms of Coulombic efficiency, 99.5%. So it's very big surprise to us. This molecule works well as solvent. So, and then we go deeper into that. It's using cryo-EM, I'm going to mention in a minute. And we can find out the SEI layer is a lot more uniform. It's amorphous, it's very thin SEI. The lithium metal deposition, the grain size is bigger. The coordination solvation shell of this lithium salt with this FDMB is very special. You notice right here, this is FDMB with lithium salt in there. This has color. The usual lithium battery electrolyte has no color. The reason is through simulation, we found out lithium coordinate with anion and with FDMB with fluorine and oxygen, forming this ring molecule. It's a ring molecule right there, you see. And this ring molecule somehow creates certain degree of resonance, electron resonance structure, and giving you this color. You know, the absorption giving you this color, it's very, very interesting. This is a complete surprise. That we wouldn't expect this would take place. So this is due to this very interesting solvation structure. So we are going deeper right now in understanding this. So let me also share with you to invent the batteries. You know, there's a possibility in every component we can reinvent. Let me just show you one example of reinventing the current collector. It's actually possible. You know, current collector is copper foil, aluminum foil. So recently we say, well, let's replace this metallic current collector with plastic, but on top of that, coating a thin layer of metal, copper, top and bottom. Inside this plastic, this allows us to embed the functions as a fire retardant in there. You can put in a lot. And once the battery about to catch fire, the temperature heats up. This to come and release the fire retardant, make the battery completely safe. And you say, why don't I dissolve the fire retardant into the organic electrolyte? You could, but you are limited by the concentration. Fire retardant made the electrolyte very viscous. So by putting into current collector, we can make it lightweight and really enhance the safety a lot. For example, a current collector we made right here is a PI polymer with TPP fire retardant in there with copper coating, right, 500 nanometer. And we can reduce the weight per unit area. For example, 9 micron copper will get to 8 milligram per centimeter square. Now with this fire retardant plastic current collector, 9 micron we get to less than 2 milligram per centimeter square. We have 5 times lighter current collector, right? In the same time, embedded fire retardant make it much safer. But certainly the things we need to consider is it conducting enough for fast charging? And this 500 nanometer, we can roughly go to, you know, CO2 1C charging. If you want to charging faster, of course, copper will need to be thicker. So using this 5 times lighter current collector and the energy density of the full battery per unit weight, we can improve by about close to 20%. In the last couple of minutes, let me share with you, to understand the batteries, we need new tools. Because a lot of materials are very fragile. This is a case of metallic lithium inside TEM. As soon as you zoom in a little bit, you see this material get melted away, they're gone. And we need a new tool for doing that. So many of you know, in 2017 Nobel Prize is given to the cryo-EM. You know, these 3 gentlemen, along others, to develop this tool to freeze the biomolecule. to stabilize that. And using the electron detector, use low dose imaging to collect the image without damaging the sample. And then there's thousands of these images taken and doing the imaging processing to get out the information or structure down to 2 angstrom resolution. And now the resolution is even better than 2 angstrom. So this was the tool in early days. I talked to my student, I said, this could be used for our battery research back in 2016. And we developed a methodology of cryo deposition and then plant freeze and doing the cryo transfer without exposing to the air into the TEM, stabilize the sample. And this allows us for the first time to really obtain very exciting information. For example, this lithium metal, dendrite, is stable inside TEM under the beam for quite a long time, turned out to be. Compared to the biomolecule, it's metallic lithium. And then for the first time to obtain atomic scale resolution of lithium metal. Lithium metal has melting point about 190 degrees Celsius, right? As soon as you focus your beam under the normal TEM, you're going to damage that. But in the cryo condition, we were able to obtain atomic scale resolution. And also, this also allows us to look at the SEI, solid electron interface, stabilize the interface, study that. There are 2 models of what's the SEI structure right there. And this certainly are the debate. And we use that, the cryo-EM, to resolve the SEI structure down to atomic scale resolution with 1 electrolyte carbonate without fluorinated carbonate. We find out it's more like mosaic model, right? It's actually more like matrix. It's inorganic particle embedded into this organic matrix, about 20 nanometer thick. So, and if as soon as you add in fluorinated carbon such as FEC, it becomes a multi-layer, in this case, bilayer model with amorphous layer, and then at the top is inorganic coating beautifully, uniformly. We could correlate the electrochemical performance with the SEI structure for the first time as well, and find out this multi-layer model is actually working so well, and you need a uniform SEI. So this went on and on. I know my time is running out. So let me emphasize the cryo-EM offer a really powerful tool. In a group along in the past 3 years, we published this number of papers, many observations. It's the first time explaining a very interesting phenomenon, having new discovery. And I'd also like to point out 2 other groups are doing this around a similar time, Atlanta and Cornell and Shirley in UC San Diego, and using the cryo-EM for the batteries, for the energy materials in general. Well, let me end my talk by just summarizing, I give you multiple examples on material design actually enabled by new tools, and thinking in the nanoscale is important. Let me end my talk by thanking the whole research group and the Battery 500 Consortium and the BMR for the support, and the DOE BES Material Science Division for now supporting the cryo-EM research. Thank you very much for your attention. I understand the Q&A section will be at the end, and I'll pass on back to Cal.
Thank you, Schultz, for this outstanding talk. We really appreciate it.